In Chapter 12, now we're going to be getting into statistics, and 12.1 is sampling techniques and misuses of statistics. So before we get into those, let's go ahead and get some definitions out of the way. So we have data. Data is information from observation or measurements, and statistics is going to be the science of collecting, analyzing, organizing, and interpreting data. So the two main types of data sets that we're going to be working with are population and sample. The population is going to be the collection of all outcomes of interest, and the sample is going to be a subset or a part of the population. So a sample should be representative of the population as a whole. So data can be used to draw conclusions about the population, and to do this, it has to be collected using a random sampling method, which we'll get into in a little bit. So let's do a couple examples for identifying the sample and population. So the first one we have, in a survey, 614 out of 1,000 business owners were asked whether they thought their company's Facebook presence was valuable. And we want the sample and the population. So the sample, it's 614 out of 1,000. So the sample is going to be 614 business owners. That's going to be the part out of the whole. And then the total amount of interest is going to be 1,000. So that's going to be the population, 1,000 business owners. Okay, and now for the next one. We have the age of 50 state senators is recorded. So the sample is going to be the age of 50 senators. And the population, so the population is going to be all the senators' ages. So the age of all, and there's 100 state senators, the age of all 100 senators. Okay, so hopefully easy enough for that. Population, all outcomes of interest, and the sample is a part of the population. Okay, for the next thing is branches of statistics. Two main branches we're going to be working with. We have descriptive statistics and inferential statistics. For descriptive statistics, this is going to involve organization and display of data. And for inferential statistics, this is going to be using a sample to draw conclusions about the population or make decisions for the whole population. So inferential is making inferences. So that's descriptive and inferential. So let's do a couple examples. So let's determine which part of the study represents descriptive and what conclusions might be drawn using inferential statistics. So part A, a large sample of men aged 48 was studied for 18 years. For unmarried men, approximately 70% were alive at age 65. For married men, 90% were alive at 65. So let's take a look at these descriptive statistics first. So descriptive is going to be the actual data that's given to us. So the data that's given to us is that for unmarried men, 70% were alive at 65, and 90% of married men were alive at 65. So the descriptive statistics is just the data, so we're just kind of rewriting the data for us. And now for the inferential statistics, now we need to try to draw conclusions based on this data. And one conclusion that looks like can be drawn is that being married is associated with a longer life for men because 90% that were married were still alive and only 70% that were unmarried were still alive. So I used the word associated. I didn't say that being married caused them to stay alive. The word associated is important here. Okay, and then one more here. In a sample of Wall Street analysts, the percentage who incorrectly forecasted certain earnings was 44%. So for the descriptive statistics, we want the data. The data says that 44% of the analysts were forecasted the earnings incorrectly. Okay, so that's just the data that's given to us. And then for inferential statistics, we want to come up with a conclusion based off of that data. And one conclusion that looks like it can be drawn here is that the stock market is just simply difficult to forecast. Okay, so that is descriptive versus inferential statistics. So now let's move on to our random sampling. So an unbiased sample is going to be a sample that is a small replica of the entire population, which is what you want, because if you're going to choose a sample and make decisions for the whole population, you want that sample to be representative for the whole entire population. And in order to have a sample to have the best chance to represent the population as a whole, the sample needs to be random. So the definition of a random sample is that every member in the population has an equal chance of being selected. Okay, and there's going to be several different ways that we're going to go over for how to acquire a random sample. And these sampling techniques are a simple random sample, which we abbreviate SRS, a stratified sample, a cluster sample, and a systematic sample. So let's start with a simple random sample. A simple random sample is going to be when every possible sample of the same size has an equal chance of being selected. So the way that we're going to be collecting a simple random sample is each member in the population is going to be assigned a number, and then we're going to use a random number table to choose the members. Or we can also use some computer software for a random number generator, and we're going to have to ignore the numbers that have not been assigned. So let's go ahead and see how this works here. So there are 731 students in a school. Using the SRS method, form a sample of 8 students using the following string of random numbers. So we have 731 students and we want 8 random students for a sample. So what we need to do is we need to assign numbers to the students. So we have to assign numbers from 1 to 731. The trick to remember here is that since 731 is a 3-digit number, that means 1 has to be a 3-digit number as well. So 1 written as a 3-digit number is going to be 001. Okay, so let's figure out who our students are going to be using that random string of numbers. Okay, so what we do is we go left to right and we read these off in threes. So our first one is 926. 926 is not in our range of numbers from 001 to 731, so we ignore it. And then we have 307. That is in our range, so whoever was assigned 307 is going to be part of our sample. And notice that these are chopped up in groups of 5 in our random numbers here. That's only for a visual. It doesn't represent anything else other than a visual aid. Okay, the next one is 824. 824 is not in our range of numbers, so we ignore it. And then there's 019. Student number 19 is going to be part of our sample. There's 267. Student 267 is part of our sample. 954 is out of our range. 575 is going to be part of our sample. 349 is part of our sample. 723 is also part of our sample. And 894 we have to skip because that's out of our range. And then 377. And lastly, we have 87. 1, 2, 3, 4, 5, 6, 7, 8. So those are the 8 students. Whoever were assigned those numbers, those will be the students that we will be using for our sample. So if we happen to get a number twice, let's say we got 307 twice, we would just skip the second one because we already had it in our sample. Okay, let's move on to the next thing, which is a stratified sample. We are going to use this kind of sample when we want to have members from each segment from the population, so we'll see what that means in a second. So the way that we're going to collect a stratified sample is first we're going to divide the population into subsets. These subsets are called strata, and the individuals or members that are contained in the same strata are going to contain similar characteristics. So once we have the population divided into strata, we're going to perform an SRS, what we just did, in each strata individually to obtain the desired amount for each sample. So let's see what these mean. So suppose we want data on people's spending habits in New York State. Using the stratified sample method, we wish to divide people into different strata. And one method to do this is divide them into different age groups. So it's by means not the only way to do it, but it is one method to do this. Okay, so splitting these up into different age groups, these are going to be our different strata for this question. Let's say we have the ages of 0 to 12, 13 to 21, 22 to 35, 36 to 50, 51 to 65, and 65 greater than 65. So once we have our strata, what we're going to do is perform SRS, what we just did in the previous page, in each individual age group. And what that's going to do is that's going to ensure that each age group is represented in our random sample. Okay, so let's say we wanted 60 people for our sample, 60 people total, and we had these individual strata here. We would perform SRS in each group to obtain 10 people from each group because there's 6 total groups. So 6 times 10 is going to give us the 60 that we need. Okay, so that is our stratified sample. Let's take a look at the next one, which is a cluster sample. So for this method, we're going to use this when the population falls into naturally occurring subgroups. So the way that we're going to be collecting these ones is we're going to divide the population into groups. This time we're going to call these groups clusters, and then we're just going to select one or more clusters for the sample, depending on how many individuals we want in the sample. So let's see an example here and see how it's different from what we just did. So same example that we just did. Let's suppose we want data on people's spending habits in New York State. Using the cluster sample method, we wish to use naturally occurring subgroups. And one way to do this, once again, this isn't going to be the only way to do it, but one way to do this is to divide the states into their counties. So divide the states into the counties. These are going to be our individual clusters here. And then we're going to choose all of the individuals from one or more of these counties as our sample. Okay, so similar to stratified, but still pretty different. In stratified, we had to split up the data, split up the population into groups that we call strata, and each individual in the group had to have similar characteristics. That ensures that all of those characteristics are going to pop up in our sample. For a cluster sample, we use naturally occurring subgroups, and then we're going to choose one or more of those groups called clusters for our sample. Okay, let's take a look at this last one here. We have systematic sample. For this one, we are going to be choosing members at regular intervals. So the way that we're going to be collecting this is we're going to assign a number to each member of the population, and the members are going to be ordered and then selected at regular intervals, meaning every certain number of people, we're going to select somebody. So every kth member, K is going to be the number in the total population divided by the desired sample size. And when we're doing this calculation, there's a chance that we may need to round to the nearest whole number. Okay, let's see an example here. So let's say we wish to choose 20 houses from a street with 100 houses on it using the systematic sample method. So we can go ahead and figure out what our K value is going to be. It's going to be the number in the population, which is 100. The houses on the street are the objects of interest here, divided by the sample size, which is going to be 20. So 100 divided by 20 gives us 5. So we are going to choose every fifth house. So let's say we have these X's here on the street. These X's represent houses on the street. So we don't have to assign numbers to them or anything and put them in order because they're just naturally in order for us on the street. So we're going to choose every fifth one. We can start with the first one, and then we're going to end up choosing 1, 2, 3, 4, 5. This will be the next one. And then 1, 2, 3, 4, 5. That will be the next one. 1, 2, 3, 4, 5. That will be the next one. And then I just put ... for and so on. So we just choose every fifth one. Okay, and for the little note here I put at the bottom, if there is a pattern in the order of the members, then doing the systematic method here will ruin randomization. Okay, so there is a possibility that we can do some bad sampling. Our samples will not represent the population as a whole. And two of these are convenience sampling and bias sampling. For convenience sampling, that's going to be that members in the population are just easy to access. So let's say we're doing some sort of survey. And an example of convenience sampling would be asking friends in a survey. So it's obviously very convenient. You can just text your friends, call your friends up, and ask them to take part in this survey, but it may not represent the population as a whole. And then for the other one here is a bias sample. So a bias sample is when some members are purposely left out or purposely included in the sample. And a pretty good example of this for a bias sample would be the presidential approval ratings. So chances are if you're flipping over between certain news stations, the presidential approval ratings are going to be different. And that is most likely because the sample that they chose was a bias sample. They purposely included or left out some members for their sample. So that brings us to the last thing here with misuses of statistics. So statistics is obviously very valuable in many different disciplines, but it obviously gets misused by individuals, businesses, advertising firms to try to either sell things or further their agenda. So anytime that you're presented with a statistical statement, you should examine it carefully before accepting it as fact. So two of the main questions you should be asking yourself when presented with some sort of statistics is, was the sample used to gather the data unbiased, and was it a large enough sample size? And the other question to ask yourself is the statistical statement ambiguous? Meaning, can it be interpreted in more than one way? So for example, there's words like average that get thrown around or largest that get thrown around. So these can mean different things. Average, we'll see there's going to be several different ways we can calculate an average, and largest can mean many, many things. So let's see a couple examples here of statistics being misused. So in this first example, in an advertisement for golf balls, a driver golf ball is hit and another brand golf ball is hit in the same manner. We're told that the driver golf ball travels farther, and we're supposed to conclude that the driver golf ball is going to be the better golf ball because it traveled farther. So for this advertisement, it does not mention the number of times the experiment was performed, or if they were results from earlier experiments. Conducting the experiment one time would not be a sufficient sample size. And it also leaves out important variables like wind speed and direction, and the fact that no two swings are going to be perfectly identical, and the ball may have landed on different surfaces. So let's take a look at another one. So Hardings claims that it's the largest department store in the United States. So that's that word largest that we just mentioned a few seconds ago. We don't know what that means. Does that mean that it's the largest profit, largest sales, largest building, largest staff, largest acreage, or largest number of outlets? We don't know because it is not specified. Okay, and then the last one here, let's take a look at a graph. So taking a look at this graph, we clearly see on the horizontal axis 2013, 2014 on both of them. The first one looks like there is this very large increase between 2013 and 2014, whereas the one on the right only shows this little increase. But if you actually look at the vertical axes on these, they're actually the same increase. It goes from 95 to 100, and this one also goes from 95 to 100. So the scaling is different. So for whatever reason, whatever these graphs represent, it could have been used to show that this was a larger increase than it should have been, or maybe it could have been shown that this was a smaller increase than it should have been, depending on what the context of the problem was. So the same exact graphs, but we can see that the scale change makes them look quite different. Okay, so that is it for this chapter.